Okay, good afternoon to everyone on Zoom. Can you hear me well before we begin? Just to make sure on Zoom that you can hear me well before we go ahead and proceed. Okay. Thank you, Ian. Thank you, Johan, for confirming. Go ahead and share the screen. Switch over here. Okay, so we can go ahead and start. Good afternoon. Not sure what that's doing here, but it's there. So yeah, happy Monday. Yeah, we'll speak a little bit about course logistics before we begin our lecture. So just to keep in mind that assignment three has been already been out, I think from last week or since that announcement has been out, and that will be due the 23rd. So that's the day before the final exam. So that's a Sunday, and then keep in mind the final exam will be on the 24th as it was voted. So where are we at in the modules? We're currently in week 14. So today we're gonna continue um, chapter 5, which is the network layer, but from a control plane point of view. And we hope to wrap chapter 5 this week, and then the final exam will be chapter 5 will be part of the final exam. So next week we'll have the midterm on Monday, so there's no class. And then obviously Wednesday we're off for Thanksgiving. Okay. And then last week, which is going to be the 16th, that's from the 1st to the 5th. There's no lectures, it's final week. And that week is just going to be used for grading and making sure that everyone grades are in and all that is taken care of. Okay. Is there any questions? No? Okay. One more thing that I would highly appreciate of you guys is to fill out the SPIs. And there's extra credit that is going to be involved with those, as I announced in the recent announcement. Um, Basically, they're anonymous, and it's just basically a peer evaluation from the students to the instructor. So I think when you log into your ucf.edu, it should show up there, and it would require you, not require you, I think it's optional, you can skip it. Um, and if you don't want to do it, you don't have to, but basically just write about what you liked about the class and didn't, and like what do you like to change? Maybe something that should be removed, revoked. So that is all like all feedback that is going to be very beneficial for me for my future teaching career. Okay, so um, it'll be 4 extra points for if 90% of the class completed. So that is optional and up to you guys. So let's continue with chapter 5. So last week we go a little bit to chapter 12 because it's really important. Once we started the application, sorry, the network layer from a control plane, we talked about the Dijkstra algorithm, and then chapter week 13 for the second lecture of chapter 5, we talked about distance vector algorithm, and we talked about the Bellman-Ford algorithm. So that lecture was on last Monday, the one that was recorded. I highly advise that one to be watched because these two lectures are kind of like the fundamentals for chapter 5, link state algorithm and distance vector algorithms. Okay. And then last Wednesday, we discussed OSPF and BGP. Those are going to be the actual protocols, you could say, or the actual algorithms that are using those intrinsic features that we discussed. So we started with OSPF, and we said that there's need to for the routers to be communicating with each other. There needs to be going to be some sort of algorithm that's going to communicate with the routers. Like how does the router forward the information based on? So we know that there's two specific approaches like link state or distance vector algorithms. Then we reached a point where we have to differentiate or have a distinction between intra-AS and inter-AS. So intra-AS is going to be all routers in the same autonomous system. Um, they can have, so it's basically, you can think of as internal and external. So internal is all the LANs, all the local devices within the AS need to communicate with each other. So they communicate by using the same algorithm. And then inter-AS is going to be inter-domain. So when those different ISPs or different autonomous systems need to communicate with each other, they also use a specific algorithm. So that allows to have segmentation and more control of the internet, and allows flexibility for the organizations to run different algorithms. So we did this last lecture, I think, and once you ping any specific host and get their IP address, you can use the autonomous system lookup and see where this IP address belongs to. Okay. If it's internal or external traffic, like internal or external traffic to be sent out, it's also going to be stored in the forwarding data. So intra-AS is going to be something that is going to be local, and inter-AS is going to be for, as you can see, the red arrows for external routing. Okay. Here we gave a human analogy. Intra-AS is like driving with your neighborhood. You know all the rules. You kind of know all your neighbors. You kind of know everything, all the shortcuts. And inter-AS is going to be like travel between cities or states. So you rely on highways such as BGP. So we did discuss PGB and OSPF. So we discussed OSPF for open shortest first path, and we talked about the hierarchical way it works. And then we moved on to BGP, and BGP kind of works externally, connecting these external points. We talked about eBGP and logical IBGP, and how routers would communicate with each other internally and externally in the last lecture. We also talked about advertisement, meaning that if a router comes in, like here, router X, for example, and joins this autonomous system 3, how does it advertise itself to AS2? Okay, so we talked about advertisement. Then after advertisement, there's going to be kind of like challenges with the routes, because we're going to have policies that are set standard by the ISPs or by the autonomous system. So we also must comply with those policies and the paths that we have available to take. Okay. So for example, if X joins the autonomous system 3, and we want to deliver a path to autonomous system 2 to say, hey, to reach X, you can contact AS3. And these are going to be the bridge routers, which are 2C and 3A. So if we want to contact X, we have to reach the bridge router, which is 3A. Then we are reaching the autonomous system 3. So here, once we reach the AS2 using 2C as a bridge router, we would distribute the path to get to X to the local routers, and then it would transfer from one autonomous system to another. Okay. So for example, if we're here at 1A and we want to get to X, there's going to be two kind of algorithms that we take, or two kind of steps. First is we take the local. So we use open shortest path. It uses link states. And we want to know the quickest path to travel locally. Then when we get to external, this is outside the autonomous system, we are using BGP for outside traffic. The lecture that we talked about last week is very more in detailed, that contains everything that we have. And see here, autonomous 3 can have two paths for advertisement. It can have one through here, then it goes to AS1, or it can have a direct link. And these are the messages that BGP would advertise, or kind of like the notions that come with BGP. This talks about advertisement and how we can keep a local kind of routing table. We also talked about hot potato routing, which is going to be, um, it chooses the local gateway that has the least cost. It will always choose the least cost. So if we compare the paths, for example, we want to get to X, and we have two ways to get to X, and we're at 2D right now, router 2D, and we want to get to autonomous system 3 or router X. We have two ways to take it, by by initially looking at the weights. There's a higher cost here to get to router 2C, but it takes us less steps. So the hot potato routing would take the least cost weight. So we'd go to 2A, 1C, and then 3 and AS3, reaching 3A. Here we talked about policies when it comes to provider networks like ISPs like Spectrum, AT&T, Verizon, and then we have customers. How a customer says, I don't want to be used as a middleman for other ISPs to deliver traffic through me. And then B, like Spectrum can say, hey, I don't want to act as a middleman too. So there's policies that's also involved with the routing that we talked about. So yeah, that was it for last lecture. We talked about OSPF and BGP. Today's lecture, we'll talk about SDN. I know we talked about a lot about SDN, but this is kind of like in relation to the control plane, not the data plane. And next lecture, we will talk about ICMP, the Internet Control Message Protocol, and then we will talk about network management configuration, and that should wrap up chapter 5. Okay, let's see here. Okay, so as usual, the slides, some of the slides are borrowed from the book and they can be retrieved using that link. The lecture is also being recorded. Okay, so where are we in the current roadmap? We reached the highlighted point, which is software-defined networking control. So we'll talk about the traditional distributed routing and how it separates control logic from forwarding hardware. And then we'll talk about the software-defined architecture. We'll explore centralized control uprate. Since software-defined networking is an open kind of open state protocol, we see that there's a lot of different architectures using software-defined networking that has been kind of like published and are being used. So they're kind of like fine-tuned or tweaked in a way. And we'll also talk about those. So before to talk a little bit about historical base of the internet and to give you an idea how the internet started. Initially, we know that it was a per router control approach, meaning that each router had control over its own decisions. So routing algorithms like protocol implementations, forwarding logic that all lived inside the same physical router. So this worked very well when networks were simpler and smaller, but we know as network grew, the limitation there become a limitation of this approach, and it became very noticeable. So innovation depended entirely on the hardware vendor since the software was closed. So if we wanted to update the routing behavior, required firmware updates or buying new equipment. So what made us shift from the traditional routing to kind of like software-defined networking is that traditional routers were monolithic systems that contain both switching, hardware, and control software. So vendors bundle everything into an operating system such as Cisco iOS. So the OS implemented routing like RIP, ISIS, OSPF, or BGP. And because of the model that we had with this, networks were tightly coupled to vendor decisions. Okay. So experimenting with routing ideas or having new algorithms was extremely difficult because performance, features, and flexibility were limited to by whatever the vendor has exposed us to. Okay. So we jump to middle boxes. So we know that middle boxes anywhere there's going to be in the infrastructure of the network, such as NATs, firewalls, load balancers, IDSs, and as those were added, and we had other appliances that were deployed, we need a way to configure those. We cannot really have a configuration for each one of those. So that increased the complexity because each device would need individual attention. So then automation became hard to control since there's not a unified way to control all these devices and have control over them. So scaling was hard. Troubleshooting was also hard to do when we are dealing with the traditional way. And then around 2005, researchers and industry groups began rethinking how network control should be or how we can make it better. So the growth of large data centers and cloud services um, highly had a need for programmability. So operators wanted to change network behavior without replacing hardware. So that would decrease cost. And there was demand for more open, flexible way to manage those devices. So earlier projects, I think like Ethane or OpenFlow pushed the idea of spreading the control plane from the data plane. And that later shifted to software-defined networking. So this is a slide that determines like the traditional approach that we have. So here we have a variation of routers. Um, we have variation of routers, we have paths, and we know once a packet reach, we have specific algorithms that would be used to find the best efficient path for routing. When it comes to the idea of how we take the routing, each one of those routers would have like kind of a cylinder that would contain or kind of highlight that it controls its own logic for each router. And then we had local forwarding table inside each router. So each router here had its own local forwarding table. And this contains when a datagram arrives, it would examine, take a look at the headers and see where it would forward it to. Okay. Now the routing algorithms here are going to be within each router. So we can have a routing algorithm different for each given router. Okay, and that is going to be installed firmly on the router. And then the routing is obviously going to make decisions based on a local forwarding table that we have installed. And then the control plane would be the routers, and the data plane would be the actual devices that would forward that data over. Now we move to software-defined networking. We have the same image here as well. And the idea here, we have individual routers, okay? And here it changes to having a remote controller, which is the idea where software-defined networking came in. And this controller kind of has like a global view or a big view of everything in the given network. So it knows that there's several routers exist and knows the local table for each router. So it takes control over everything. So it becomes more unified. The local tables for each router is going to be also within the remote controller. So that's how we know how we can forward or send the packets over. We have the CA, which is going to be communication channels between the controllers and the routers. They would communicate with each other. So the controller here would monitor the network and send updates to the controller. And then each router is going to have a CA, kind of like a controlled agent that communicates directly with the controller. And here's the separation. Is the same exact separation, but here it just got replaced by a remote controller. So you might ask yourself, why a logically centralized control plane? We know that SDN, software-defined networking, introduced an idea that is centralized control plane that has a view and manages the entire network topology instead of each router making its decisions independently. So the controller oversees the full topologies. This reduces the configuration errors and helps enforce consistent policies across all devices. So it gives operators more direct control over their traffic. So the first thing is centralized control across the network, and it's easier to manage. Okay. Second thing is that table-based forwarding, such as OpenFlow, allows the controller to program switches with specific forwarding rules. So centralized programming became very easy because the controller computes the tables using the network information that we have. So the idea of distributed programming is harder since each router must compute tables on its own while staying consistent with others. So centralization gave a more predictable behavior and simplifies troubleshooting. And like we said, SDN encourages open, non-proprietary control plane design instead of a locked vendor system. So this opens the door for experiments, research, and rapid innovation of software-defined networking. So the idea has opened many solutions for us, and can emerge when the logic is accessible and programmable. So that led to the growth of software-defined networking. Here to give you an analogy of mainframe to PC revolution is that early computing relied on large vertical integrated frames. We have like hardware, operating systems, and applications. And we're all tied together in one closed system. So this resembles how traditional routers bundled all functions tightly inside those devices. And innovation was slow because only vendor could change or extend the system. So the specialized applications is going to be mainframes that required applications specifically designed for that particular hardware and operating system. So that limited the types of software that is available and slowed down adoption. And that is similar how to traditional routers needed vendor-specific features or updates. The operating system was also tied to the hardware. So only the vendor controlled the updates, features, and capabilities. And the specialized hardware that we have is that mainframes would run on custom hardware that was expensive and difficult to modify. So there's no standard interface for others to build on. Okay. So let's see how this shift has happened. So we would have open interface for hardware, so microprocessor revolutions. The shift began when hardware was open through standardized interfaces. So anyone can build around the same microprocessor platform. Okay. So this kind of segmented the hardware from the rest of the stack and allowed rapid evolution. We have also now open interface for operating systems, Windows, Linux, or Mac operating system. And they became like interchangeable choices that we had available. So that kind of like illustrates the powerful of having separated layers and letting each one evolve independently. And then for applications, since OS has expanded choices, applications can run on the same hardware platform. So software became the main driver or the main innovation point instead of the physical machine. So that created rapid and evolution change in the industry. So here we kind of give a few examples of difficult traditional routing that we have. So here we have, I think this figure we have seen many times with the Dijkstra algorithm or with the Bellman-Ford algorithm, where we have a router, many routers, sorry, and then we have a server and a host. And currently, the host is reaching the server, taking this path through U, X, Y, and Z. Obviously, each node that is connected with each other has a link that is associated with that. So traditional routing selects the shortest path on the link plate. That's what we take. So operators get very limited influencers over which exact path they should take. So that path right here is taken in red is by the traditional router. imagine if we had an issue. What if the network operator wants to take the other path instead of this traditional path that we have? So we want to take UVWZ rather than UXYZ. Okay. Traditional routing does not directly allow this kind of path control. Cannot really do anything with that. So the only way is to force a different path, and this is going to be to manually adjust the weights. So this is a trial and error messages and can affect many other routes. So it's going to be a very difficult way to tune the link weights without causing intended consequences. So it's not an easy thing that can be done. So the idea here is that with traditional routing has limitations. Those limitations were replaced by the software defined, and we'll see how it can manage something like this, where the controller has direct control over the paths instead of relying on the weight tuning. And we have here the same figure, same topology, where traffic is flowing from U to Z. And we know that there's two possible paths, like using UXYZ and using UVWZ. So we have a top and a bottom path. And we know that traditional routing would choose directly the shortest paths. And what if we wanted to split the traffic? Meaning that we wanted to split the traffic on the top path and the bottom path. So like, for example, load balancing, and we have talked about load balancing, and it's kind of like a middle box that we have, and that could be a feature that is embedded in web servers, or we can have a specific device for load balancers, is that load balancer would say, hey, I have the incoming traffic, I can balance it out where not both routers are exhausted, not one specific path is exhausted. So that can be something that is done to avoid congestion and to avoid exhaustion of those routers and servers. So this is a common engineering tactic, or you can say way where we can split the traffic to avoid congestion or better network use. So traditional routing also doesn't support that. And you cannot actually split the traffic using standard link state or distance vector routing. So the algorithm selects one deterministic shortest path. So to achieve load balancing, you would need a different routing algorithm or a completely different one control mechanism. So the limitation is one of the reasons SDN became attractive, because you can kind of have explicit control also based on algorithms that can influence these paths that are being taken. The same figure here we have, and the question on this one, it says, what if W here, the blue is wants to take a different path than the path that we have here as well. So what if we want to split or differentiate forwarding? So like the red traffic could go through one of the paths, and they can go like vice versa. They can like kind of intervene with each other. So traditional routing also does not support this behavior, and these protocols do not allow you to do anything like that. So we learned in chapter 4, where generalized forwarding, that we have MSDN can be used to achieve any routing that is desired. So this kind of just shows you like some limitations of traditional routing and how software-defined networking came and changes. Okay. So traditional routing focuses on computing the shortest paths based on link weights, and that's going to operate very well for basic connectivity, but can make traffic engineering very limited. So routing decisions, where we have exactly routing is destination based. So routers ignore flow type, load, or operator intent. So if you want to use traffic, you just have to use the path that is available or adjust the weights. But we know how adjusting the weights can affect that. So those small weights changes can cause large unpredictable shifts. So it's harder to adapt to congestion or failures. And is where we lead to software-defined networking. Okay, so this shows the basic architecture that we have. Um, the first thing that we want to talk about is the lower part. This represents the data plane, where switches would just simply forward the packets. Okay, so their job is just to forward the packets. The upper part is kind of like the brain we have, where the controller runs routing, access control, and traffic engineering logic. So we know that the controller has a global view of everything. Okay. First thing that we have here is generalized flow-based forwarding. So the software-defined switches uses they're obviously going to flow tables of traditional destination-based forwarding. So that still exists. And these tables can match fields, and we know how we can match the fields, maybe by using all this prefix matching. We can use a source, destination, we can use a port, maybe a protocol or application. Anything that we can match with the incoming datagram, we can forward, okay? So one example of generalized forwarding is going to be OpenFlow. And we have here the control plane separation. So this dotted line here is going to be the point of separation. And this is going to highlight that switches no longer run routing algorithms. And that is just like to show you that it's been taken over by the control plane. And at the control plane, we have functions that live outside the design, that live outside the devices controller. So this includes, like routing, access control, load balancing that we can see here. And then we know that it has a global view. And then also last thing is programmable controlled applications, and where we can run custom applications that runs in these controllers. And those are going to be programmed based on specific routing policies or advanced traffic engineering, or based on the admin choice. And then we can have new features that can be added in the software without changing any hardware. So now we just focus on the data plane switches for now. So those are the devices here in the lower layer that handle just data forwarding. So the controller is going to handle all the decisions. Okay. So the diagram on the right here is going to show that we have switches and they're above connected to the controller. Why do we have this separation, and what is the benefit, or maybe the pros? First is going to be very fast and simple. So they're going to be very simple and efficient just to forward at a high speed that don't run into complex control problems. So the forwarding behavior is going to be generalized such that data planes are implemented directly in the hardware. Flow tables are installed on the controller. So the controller has all those localized tables, and it does the computation for them. So this ensures that the switches follow the policies rather than running their own routing algorithm. We have API for table-based control, which is going to be OpenFlow. So this is a common API to configure those tables. And lastly, we have protocol to communicate with the controller, and this is going to be using OpenFlow as well. So this protocol allows to send live updates, newer flow table updates, statistics, and even event messages. So it keeps the controller to fully know of what's happening. Now we move into the software-defined controller, and this is going to be in the middle. And this is it's gonna be obviously like the operating system of the whole network. Okay. Above it we have the network control application, and below it we have the switches. We know that the controller maintains network state information. So it has a global view of the network. That means it has all the topologies, it has link statuses, it has switch statistics and traffic patterns, and that can make it allowed to make routing and policy decisions. Um, Applications route like routing that we have on top, or access controlled or load balancings, um, can be typically be done using OpenFlow. So this is how the controller would enforce decisions across the data plane. And we have distributed system implementation. So a single controller is not going to be enough for large networks. So in practice, there's many controllers that are going to distribute it and implement it that can achieve high performance and less fault tolerance within the given network. Okay. And then lastly, we go to yep, for robustness. And then lastly, we go to the network controlled apps. And these are going to be the top layer. These are then that implement the actual control logic. So like routing, access control, or load balancing. So the applications are the brains of the control plane, and they're going to use the north bound API here to gather network information or push new forwarding rules. Um, Software defined would allow unbundled, meaning that they don't need to come from the same vendor. So third party or organizations can develop their own routing or security policies or applications. So that is what we have. So this slide breaks down the main components, um, internal components of the software-defined networking. So the diagram shows three layers that we have. The first one we have is communication, and this is the bottom one. We have the second one is state management and the interface layer for the applications. And basically, this is what we talked about when we are diving internally into each specific phase. So the first thing is the communication layer. This is going to handle communication from the devices to the controller by using OpenFlow or SNMP to deliver newer rules, gather statistics, and even event notifications. So this ensures that it's kind of like a three-way communication between the layer one to the two to the three, obviously, because we know the controller needs to have a global view or make sure that it knows everything with the given network. And the controller is going to keep kind of like an active directory, or you can say a distributed database that contains all the network information like link state info, host info, switches info, flow tables, also statistics. And the state is going to be synchronized across the controller for reliability and scalability. And the top layer we have is exposes the APIs and abstractions to these applications. And apps interacts with the controller using APIs like REST here, or intent-based yeah, this is going to be intent-based or REST API. And we also have this enables also third party. The top layer also enables third party or custom applications being done to it. Is there any questions so far? Anything unclear? Okay. Let's talk a little bit about OpenFlow. And this is the main protocol for communication channel between the controller and all the switches. So OpenFlow would carry all the messages and tell the switches how to handle packets. So this diagram what we have is we have the controller uses OpenFlow. It would distribute messages to the routers that would take those traffic decisions. Okay. The first thing that we have to know is that for security or reliability, we are also using TCP. So TCP is going to be used almost everywhere that we have. So between the messages between the controller and each connected switch are going to be travel over a connection, a TCP connection. And there also encryption can be enabled using TLS for secure environments. So that ensures that controller can push rules and receive events consistently. There's going to be three classes of OpenFlow messages that we have. So we have controller to switch, and this kind of like instructs to kind of add or modify or delete flow entries. So this is kind of directly from the controller to the switch. We have asynchronous messages that is going to be switched to controller that notifies like the controller of events like port changes, packet arrivals. And we have symmetric messages that are going to be general messages that are exchanged in both ways, such as keep alive or feature requests. So these are the message types that would allow OpenFlow to work with the controller and those routers. Um, we have distinct from Open API, from OpenFlow API. So this shows that the OpenFlow is the protocol, and it can be used by various applications, and this is going to determine the forwarding actions and match fields. So these are the messages that we're going to talk about, key controller to switch messages. We'll send to those. So here we have the same figure of the controller here sending messages down or up to the server using OpenFlow. So the first thing it would send features. So the controller would start asking or kind of like querying for um, asking each switch what it supports. And like this is like number of ports, table sizes, match fields, and supported actions. And that kind of gives or helps the controller know the switches and how to program those switches. The second thing is to configure based on the features. So it can set any like specific parameters, or it can enable or disable ports or adjust those modes within the switches and configure how each switch handles packets and how it can mount. The modify state as well. So this is like the most important message for the software-defined networking. And this is going to be like where it adds or deletes something. So this is going to be like modification. And then packet out. So the controller can directly send a packet out of a specific switch port. So this is used when a switch forwarding is unknown, or a special packet to the controller is packed in. So like sometimes there are packets to be sent, and the router does not know what to do with them because maybe um, there's really no kind of information that can be compared against the table that we have, the local table with the overflow. So it would send it back to the server. Okay. And the server would take control of it. So it's going to be manually be sent in essence. And then we have key switch to controller messages. So this is going to be first thing that we have is packet in. So this is going to be a message that is sent when a switch receives a packet that does not match any installed rule. So the switch would just forward the packet or just the header so that the controller can make a decision, as we talked about. We have flow removed, and this is going to be basically the switches notifies the controller that, hey, and you can see those messages are going up and down. There's a deleted entry at the switch, or something has been changed or removed. So we can make sure that the controller has an accurate, up-to-date view of the network. Port statuses. So the switch can also inform the controller whenever a port changes. And this includes like speed changes or port errors, anything that has been changed. Something to know about the abstraction is that operators don't manually generate OpenFlow messages. Instead, they will use higher level abstractions or controller applications. So they would automatically translate application into the OpenFlow commands. So this is how the controller kind of stays updated and is hand to hand with the local forwarding table that we have. So this kind of shows an example of how software-defined kind of operates and how they interact during a regular network event. Okay. And here in this scenario, we have a link failure that occurs at switch one. Okay. So here we have switch one and we have the kind of the layers with software-defined networking. Okay. So the first thing that we have is that switch one detects a link failure on its interface. So it would use OpenFlow to send port status messages. It's trying to notify the controller that switch one has some sort, or router one here has some sort of error. Okay. And this is going to be the part that we just discussed, switch to controller messages that are being sent. The controller obviously would receive the messages, would update the link state info. And because we know that the link state info kind of keeps track of the state of the switches and their links. So we update that so that the controller has an updated version view of the network because we have a fault with switch one. Here we're using the Dijkstra link state algorithm for routing. So this is registered to react whenever link state information has changed. So we must communicate the routing algorithm to let it know that computation has to be redone to find the shortest path or to find the best alternative path. Okay. Then the routing app retrieves the updated network graph and link state from the controller. Then it would compute the shortest paths or find new routes using the algorithm. And the results are going to be sent back to the controller to update the flow tables. So we're updating the flow tables even when there's an error and once the error is also fixed. In here, we continue the same situation or the same scenario. And here, the link state routing interacts with the flow table commutation model inside the controller. And that translates to a high-level routing decision that's going to be made. So, for example, it decides which switch gets entry and what match fields to use. And then, obviously, the controller would kind of find alternatives. So, the controller would send down rules to switches using OpenFlow, and only the switch that needs updates receive new entries. Okay. So the event completes a control loop. We have an event that is detected. We go to a state updated phase. We go to routes that are being recomputed. Then we go flow tables that are being installed. And then obviously it would go back to typical behavior, switching would forward traffic using the corrected paths. We have ODL, and ODL is kind of like one of the most widely used open source controllers. So it's built on top of modular plugin based architecture. And it also supports many network functions because we know that software defined networking with OpenFlow is open. So advancements can be made where we can have something like ODL. So ODL here is going to be basically um, the internal services of ODL. See what we have. So these are the internal services of ADL. We have something like topology discovery, we have switch management, statistic collection, host tracking, forwarding rule management. We can also have enhanced services such as AAA or other high-level modules. So these are gonna give the intelligence to operate the network. We have the service abstraction layer. This is gonna be like the glue inside the OL. And there's going to interconnect. It's going to connect here basically internal modules with external apps that we have. And here we have the northbound APIs. This is going to be like REST config, net config. These are going to allow the applications to interact with the ODL, obviously, where we have access state, push intents, retrieve information, and so forth. We also have ONOS, and this is going to be basically another major open source software-defined controller that is designed for large scale telecom and carrier networks. So we have on top, which is going to be the network applications. And there's going to be basically different for each controller that is built. Here we have load balancing, firewalling, and traffic management. We still have the northbound abstraction protocols, and we have the southbound API. So the core of it is going to be basically, it focuses more on scalability and reliability. So the core handles like hosts, paths, devices, flow rules, topologies, devices, statistics, and many more. Okay, so that is going to be the main core, or kind of like the global view of the network. Here we have the southbound abstraction protocols, and there's going to be like how ONOS is going to interact with the physical network. And here we have an idea. It supports multiple southbound protocols. They're going to be like OpenFlow is one of them, NetConfig or SDB. These are just various protocols that it can support. Here we have using REST plus intent, and these are going to be the APIs to the applications that are being used. So developers specify what they want and not how to configure the network. And here we have the characteristics or the design or behind this topology, we can say this development and the key characteristics that we are here. So applications are going to be obviously separated from the controller core. The intent framework supports high-level definitions. There's strong emphasis on distributed operation. There's also fault tolerance and scaling under larger network loads, and that is what it was originally built for. Here, this is something that is really not compared or has any correlation to software-defined networking, but we have the idea of SIGN. And when we are speaking about a little bit about security and privacy of networks, SIGN is used kind of like to collect information and collect log information about the given devices or the given topologies, and they can be used by admins to make those networks be more robust and resilient. So we know that the software-defined networking, because initially how it was, I'll jump to this slide first, just to show you how it works on a view based. SIGN is basically going to be like a server that is connected to those switches, routers, any kind of middle boxes or applications that we have. Would collect all this information, then it would analyze those information and kind of like provide them on a dashboard base, or kind of like a neat way for the admins to see. Here, since we have shifted to software-defined networking, they can also generate massive amounts of data about the switches that we have, the controllers, the virtual networks. And we know that SIGN comes in and collects, analyzes, and correlates logs. So this includes anything from here, hosts, switches, controllers. And this can help us identify events and anomalies. So like traffic patterns, misconfiguration, or unauthorized flows. And then SIGN can be configured to evaluate the level of data. So we can see any sudden routing changes, abnormal flow tables, link failures, and much more. And the effectiveness is going to depend on how well the controller exposes data. That's going to be obviously to the API that is directly influences what the SIGN can monitor. So administrators, they can go and fine tune the rules for software-defined environments, and the raw log data can be reviewed on a time-to-time basis to make sure that there is no subtle network control issues are missed by automation. And we can skip over this since we have an idea of how this works. So we have some challenges with software-defined networking, obviously, or some maybe you can say limitations. And the first thing is hardening. meaning that hardening the control plane means the controller itself is going to be dependable, reliable, and scalable and secure. So it is going to be very maybe hard to do something like this. Also, networks and protocols must meet specific requirements. So real-time control in industrial networks, ultra reliable speed, critical systems, ultra secure communications like in military or financial environments. We also have internet scaling beyond a single autonomous system. So coordination across different ISPs comes a difficulty. Handling policies, routing differences, and scalability at a global scale. And also, software-defined networking is also involved in 5Gs, where it enables maybe network slicing or provides fast recognition automation, and it supports ultra-low latency and high bandwidth workloads. So we know that SDNs have become very more widespread, and one of the big questions that we can have is how will it shape or even replace traditional networks? And we have seen that it has been replaced. So we were using distributed protocols for decades, and software-defined networking changed that model for us. So one example of the shift is going to be the tables that we have, the local tables computation. So in traditional network, each router obviously is going to run its own protocol and own table. And software-defined networking, it can be communicated centrally and pushed to every switch. So this is a clear contrast between logically centralized computation and protocol-driven computation. Another driven is the congestion control. So we have today any endpoints and it would experience something like packet loss or delay. And we have talked about how model loss can be happen or delay can happen. So routers would have to react independently, but imagine a software-defined networking is doing this globally. So it would have to adjust its rates based on the complete view of the network. So this brings like a question to think in the future is how we will implement of network functionality, software-defined versus protocols evolve. There's really, right now, there's no single answer or a defined answer to answer how SDNs or traditional protocols will evolve, but we can maybe map some direction based on what we're already seeing in real deployments. So this shift is going to be all or nothing. So most networks will evolve somewhere in the middle, where we have hybrid models that combines SDNs and distributed protocols. We can have more controller-driven intelligence in routing and congestion control. We can have protocols that are simplified into basic transport mechanisms. We can have shift towards intent-based network and automation. And finally, we can have something like growing dependence on telemetry and real-time network states. Yeah, so this is the roadmap so far. We talked about introduction, we talked about link state, where the router has a full view like the Dijkstra algorithm, distance vector, where routers would exchange information and updates its computation based on the neighbors. We talked about OSPF and BGP, and today we focused on control plane of the idea of software-defined networking. We talked about the role of the controller, how it has a network-wide state and abstractions. We talked about OpenFlow, which is the protocol that is used to exchange information from the switches to their controller. We examined software-defined applications and various deployments that have been made, like OSPN and the other ones that we have launched, that were launched. So next lecture, we will talk about ICMP and network management configuration. Okay, so that is all we have for this lecture, and I will see you all on Wednesday. So Wednesday is going to be our last lecture for the semester. and then Monday you have the final. So if you have any questions regarding anything in the class, you should use that time, maybe after class, or if you want to stop by office hours, it's going to be very beneficial for you if needed. Okay. So if you have any questions, feel free to ask them. If not, I will see you all on Wednesday. Yes. Yeah, I'll open at 12. Yeah, 24 hours. Exactly. 24 hours. And reach out to me if any of you have something that's going on and you need maybe to retake it earlier or later. So that's depending on like if you have actual reason behind. But don't wait last minute and say something came up, so we can work with you. Okay? Yeah. Have a good one.